Okay, all right. Hello, hello, hello. How are we doing today? I hope that we are doing well today. This is my sincere hope that we are doing well today. We'll see how this goes. My voice has been feeling a little shaky ever since yesterday, which I guess is unsurprising. I don't usually talk all that much. I mean, outside of my job being to talk, but I did two 3+ hour long streams 2 days in a row. So, oh, I'm glad to hear it, Astral Atropos. I'm very glad to hear that it's been a good day. That makes me very happy. It was a decent day for me as well. I can't imagine what happened yesterday to make your voice so that. I know, right? Or the day before yesterday. I have no idea why my voice feels so shaky and I almost feel like I have a sore throat. I'm not sick. I'm not sick. It's just like whenever I start talking, it's like, actually, have you considered that you talk too much? Oh no. So we're gonna see how far we get, basically. Well, I mean, I'm gonna try and make it through the whole lecture, but I cannot promise that my voice will make it through the whole lecture. Hot drink is a good idea. Okay, okay. Should I after stream, of course, but should I get tea? Should I get hot cider? Or should I get hot chocolate? I'm kind of feeling hot cider right now. I want something sweet, but like not hot chocolate sweet. Maybe I'll get some hot cider after that. Oh, I should have grabbed a glass of water. Oh well, this is fine. How do you feel about that, Mr. Kitty? He feels fine about it. Oh my gosh, I just looked at the slide deck today. It is 62 slides. What have I done? What have I done? Oh, I know a lot of them are there's a chunk of them that I'm gonna get through pretty quickly, which is something. I'm at hot chocolate right now, but it's too hot to drink. Yeah. Do you use the strategy like usually if I have a hot chocolate for the first little while I have it, I get a spoon. So you know, like you can get the spoonful and then you blow on the spoonful to cool it down, and then you drink it. I think that's the optimal way to do it. And then once it finally cools down enough, then you can just properly drink it. But I remember I used to do ice skating, and you'd get hot chocolate at the rink, and that stuff would burn like multiple layers of cells off of your tongue if you were not careful. It came out really hot. Like you would get severe burns probably if you spilled that on you. I was scared of it. It was really yummy, but oh my gosh, that thing was a hazard. You could probably melt somebody with that hot chocolate. I usually have some cold milk to cool it down, but I forgot to pick some up. Oh, that's a shame. I'm one of those freaks who doesn't drink milk in their hot chocolate. I actually think I don't like hot chocolate as much with milk. I'm the one of the weirdos who just takes my powdered hot chocolate and puts it in hot water. Some places it's just brown boiling water. Yeah, that's how I drink it. Though I do like to put whipped cream on it, of course. Whipped cream is very nice. I usually get at least two giant servings of whipped cream on top of my hot chocolate. All right, all right. Anyway, today we are talking about ANOVA, which has a very, very pretty. It's a very pretty pronunciation, I think, for a statistical test. Out of all the names of statistical tests, I think ANOVA is the one that should be used as the name of a character in a fantasy setting. I think I think it's a pretty name. Except also like I convinced somebody to name a character in one of their stories ANOVA, and now whenever I read their work, I can't take that character seriously because when I read ANOVA, all I can think of is analysis of variance, and it's my own fault. I did this to myself. Anyway, let's go. Let's do it. We're going in. So, our goal today is how do we compare differences between more than two groups? So up until now, we've been talking about t-tests. You have ANOVA. Shut up, Mari. I knew what you were getting at, and I'm like, I'm mad about. You know how I feel about puns. Don't use that against me, please. Have mercy. Anyway, up until now we've been working with t-tests, and t-tests only let you compare two groups, say like a control group or a treatment group. The ANOVA allows you to do 3 or 4 or 5 or 6 groups, theoretically as many groups as you want, which is super nice. Here's, you know how I mentioned on the Twitter post announcing this stream, I said the most forced acronym in statistics that I'm aware of, or one of the most forced acronyms. This is what ANOVA stands for: Analysis of Variance. And you can see they're taking 2 letters from analysis and 2 from variance to make this work. And they're putting the O in there from of, which is not what you would normally do in an acronym. So it's a very forced acronym, but you know what? It sounds nice. And isn't that what matters? Maybe, maybe not. I don't know. Anyway, the main difference between an ANOVA and a t-test, the thing that decides which one you would be using, is you would use an ANOVA if you have 3 or more groups. T-test can only handle 2 groups. Only 2 groups at a time for a t-test. If you have more than 2, you do ANOVA. Do you think it's less arbitrary than when only one word has double while the rest have 1? That's true. It's not like the most arbitrary acronym I've ever arbitrary forced acronym I've seen, like, you know, especially the ones where like they only take like the 2nd or 3rd letter of the word or something to make it fit. Those are painful to look at. But I have to say, I do have like a weird affection for really forced acronyms. I just think that they're fun. Like, they used to infuriate me, and now I look at them and there's just something about it that just gives me joy. I'm like, wow, this person did not want to give up on their dreams, but they weren't so determined that they found a synonym that would have worked. Like, I don't know, there's something funny about that to me. Anyway, right. So 3 or more conditions now, whereas the t-test can only handle 2. Now, because ANOVAs have more of the groups than t-tests, it's got to think about it a little different. T-test was like, is this number different from this number? But ANOVAs, you've got minimum 3 different means that you're looking at. So it's not looking at the difference between means, it's looking for the variability among the means. And the question that it's asking, it's trying to look at all the means at once. And ANOVA, like, you know, most hypothesis tests will give you a yes-no answer. It is significant or it's not. And when you reject the null on an ANOVA, when you conclude the ANOVA is significant, you have concluded that there is at least one difference between there's a difference somewhere among your means. Let's say I have 3 groups. There are 3 possible differences there: 1 and 2, 2 and 3, 3 and 1. Like, there's 3 possible differences there. If I reject the null on an ANOVA, it could be that all 3 of those differences are significant. It could be that only 1 of those differences is significant. It could be that 2 of those 3 differences are significant. I don't know what. But if I reject the null on an ANOVA, there's something there. I don't know what, I don't know how much, but there is something there. So it's just testing to see, is there anything worth digging further here? It's not actually testing which group is different from which group. It's just saying, are there any differences at all? Which is kind of sucks compared to the t-test, because the t-test is like, there's a difference here, and there was only 2 groups, there's only 1 possible difference. Here it says, hey, there's at least 1 difference here, but I'm not going to tell you how many, and I'm not going to tell you what the differences are. So it is kind of a bit more of a pain in the butt than a t-test, but that's what you get for having more than 2 conditions, I guess. So we're going to change up some vocabulary for ANOVA. And the first one, the first new bit of vocabulary, we're going to start using the word factor. A factor is... it's not exactly a synonym for independent variable. It's a very specific type of independent variable. A factor is an independent variable that is categorical. Usually nominal, doesn't have to be nominal, but it has to be a categorical independent variable. So a factor is a very specific type of independent variable, which honestly doesn't make a whole lot of difference because most independent variables, at least the ones that you manipulate, are gonna be factors. But, you know, just if we want to get really specific about it. And ANOVAs always have categorical independent variables, so the independent variable in a ANOVA is called a factor, because it's a categorical independent, it's a factor. I don't know what to... Within factors, factors have levels. So before we would have an independent variable with conditions, the conditions within a factor are called levels, and it just all feels kind of silly to suddenly start using names, different names for these things, but it's gonna make a bit more sense later down the line when we get to factorial ANOVA, but it still feels kind of silly, I'm not gonna lie. But for example, let's say my factor's hair color, the levels might be blonde, brown, red, and black, or, you know, orange if you're Psy, or whatever I have going on here, like a desaturated navy or something going on with my feathers. So yeah, a factor would be some categorical variable Levels are the conditions within that variable or the categories within that variable. So hair color, levels, major in college, the levels might be something like engineering, psychology, biology, astrophysics, or physics, or whatever. Might be the type of cutlery, the piece of cutlery you're using. So, and then the levels would be like fork, knife, spoon, chopsticks, spork, whatever. So yeah, categorical, variable, factor, and then the levels are the sort of categories within that factor. So let's do an example. Let's say I want to know, does the presentation of a teacher affect learning? So does the way the teacher presents themselves affect how effectively you learn the material? So I take 15 people and I randomly assign them to 3 different conditions. 5 people see the PowerPoint with 0 visual representation of the teacher. 5 people see a live action video of the teacher going through the PowerPoint, or a teacher going through the PowerPoint. 5 people react to the PowerPoint given by a VTuber. Bald is defined as having a bare scalp rather than not having hair, so sadly you aren't technically bald. This is true. This is true. I'm not bald. I have feathers. I'm not bald at all. I may not have hair, but I do have feathers. So I'm not bald. Anyway, right. So we have 3 different conditions. One, maybe it's even just straight up like this is an electronic voice. Oh, hello, Xenotime. Yeah, feathers absolutely count, so I'm not bald. And then in another one, we have a teacher teaching through a webcam, and then the third condition is a VTuber teaching. And then I have them all teach the same lesson on statistics, maybe the very lesson that I'm giving right now. And then we ask them 10 questions about it and see how many they get right out of 10. So the factor here, oh, I'm not actually going to say that. I'm going to ask all of you. I'm going to ask all of you what the factor is. So what is the factor in this study design? What could it be? Factors presentation style, and levels are none, video, and VTuber. Yes, correct. How the lesson is presented or who is presented by, the presentation of the teacher. Yes, all of these are correct. Our factor is the way that the teacher is presenting themselves, or I guess you could say the teacher who's doing it. So whether it's just like an AI voice reading it or like a text-to-speech voice reading it, it's a lecturer who's doing it with a live video feed, or another lecturer who's doing it as a VTuber. So the way that the person giving the lesson is presenting themselves. And we've already established the levels. Thank you, Xenotime. So it was manipulated by either having text-to-speech and no image, having a camera feed of somebody presenting the lecture, or having a VTuber present the lecture. So what people saw, and perhaps even what they heard, was a bit different. And yeah, we established what the levels were. It was no video, live action video, or a VTuber. What was the dependent variable? Let's start with sort of like the conceptual higher dependent variable, the thing that we're generally interested in, not exactly how we measured it, but what are we trying to test? Or what do we think is going to be affected by the type of teacher you've got? What should the teacher's presentation affect? How well students learn information. Correct. That is the overall conceptual dependent variable. And yeah, astrologopose is closer to how we measured it. Exactly. So the overall thing we're interested about is how well this helped them learn. And we measured it as the number of problems they got right out of 10, the number of stats problems they got right out of 10. Good job, everyone. Great job. Okay, so our hypothesis here is that the way that the teacher's presenting themselves, or the way that the teacher is presented to the class, affects how the students learn. And to test this, we probably want to see if the students in the different conditions, the students who get different visual presentations of the lecture, have different scores on this test or this quiz. So what ANOVAs do, they're a bit different than what t-test did. The null hypothesis is that all of your conditions are the same. Everybody gets the same score on the quiz at the end. Any differences are just sampling error. The alternative hypothesis is that there is at least one difference. At least one of the conditions is different from at least one of the others. So like there's at least one difference somewhere in here. If we want to get specific to the study, the null hypothesis here would be there's no differences in mean test score based on the presentation of the teacher. The alternative hypothesis would be there at least one presentation conditions test score would be different from the others. So at least one of these groups did better or worse than the other groups. It's possible all of them have different performances, but at least one is different. Literally just got a shiny shadow Scorpy, naming it ANOVA. That is the one that is different from the others. Perfect. Oh my gosh, little ANOVA the Scorpy. That's awesome. I need to fight more Go Rocket leaders, but that can come later. Okay. Bushy, welcome. Happy to have you. All right. So next, hypothesis testing. So again, ANOVAs are not going to tell us what mean is different. It's not going to tell us what the difference is or where the difference is. It's just going to tell us there a different exists. So I kind of like to think of ANOVA as like a metal detector. This is a guy using a metal detector. Metal detectors will go off to tell you that there's something metal under the ground or under wherever you're looking. That's kind of what an ANOVA does. When you reject the null on the ANOVA, it tells you that something is there, but it doesn't tell you what. You would have to go beyond the metal detector to figure out if you have found, like, metaphorically, a penny or a whole bunch of treasure, right? The ANOVA on its own only says yes or no, there's something here or there's not something here. It doesn't tell you what is there, just like a metal detector. So again, just warning here. Want to make that clear. The ANOVA on its own doesn't tell you what you found. Just tells you that you found something, but not what. So let's say we get this data. Oh, I gotta get my head out of the way. Okay, there we go. Let's say we get this data. This is our data. So again, here's our conditions. We have our condition 1, or level 1, I guess I should say, using ANOVA terminology. No visual. This is just the slides and there's no image of the teacher. Sample 2, live action. There is a live action video of a teacher. And sample 3, VTuber. There is a VTuber presented as the teacher. And these are the scores. We have 5 participants in each condition. Here's how many problems they got right out of 5, presumably, or maybe out of 6. I don't know, gosh. And then we have the means for each group and the standard deviations for each group. Now you'll notice that the means are different. If they didn't have a video, and if they had a VTuber, they only got 1 out of the 6 or 7 or 8 or 10 problems right. So that's not great. But if they had a live action teacher, they got 4 problems right on average. You didn't give yourself a very flattering score, lol. No, I didn't. I thought I'd be humble. You know? Maybe this VTuber isn't me, or maybe I'm just setting expectations. I think it's because I go on all these tangents. Surely a proper teacher wouldn't go on all these tangents. If I was actually doing this like as a lecture at V-Theorem University, like the physical campus in a physical classroom, I wouldn't be going on so many tangents and maybe the scores would be higher. But here we are. Yeah, unfortunately, it's not looking good for the VTuber thing. This does not reflect on Psi or Phi or Z or NEP, by the way. They're all lovely. V-Theorem University bans tangents, only sines and cosines allowed. Oh no! Oh no, we're doomed! We're doomed. Tangents. I'm trying to remember. Because this could be a problem. If we've banned tangents, I think we're okay. As long as we don't go into curvilinear effects, we might be all right. Anyway, where was I? Well, sine divided by cosine is tangent. Oh no. That's dangerous. All these things are dangerous. And I don't remember enough math to fully comprehend the hilarity of these jokes, because I'm like, with banning tangents, I feel the theorem theories university would very quickly run out of faculty. This is true. If we ban tangents, I think psi would simply cease to exist. Psi and I in particular, especially on our paper reading streams, we would simply evaporate. I wonder if there's something about psychologists specifically in tangents. I think phi is a bit better at staying on task than psi and I are. Z, I don't think gets as distracted by tangents, but I haven't made it to as many of her streams. Same with Nap, unfortunately. Anyway. So the means are different, right? We've got this mean of 1, this mean of 1, and that's psi 3 words per minute. If nothing else, I can take comfort in the fact that I read articles on stream faster than psi. Which I don't think is like a huge... it's not like a very impressive feat, but I'll take whatever wins I can get. Z doesn't do as many like lecture streams though. That's right, we need to wait for her series on differential equations to find out where she falls on the words per minute scale. The theorem article reading contest. Oh my gosh. We should all try and find an article and that we all read on stream and see which one of us gets through as fastest. That is a real statistic. So much. It'll be a race. I think it's better if we don't frame it as a race, so we don't have the confound of feeling like we need to get through it fast. I want to see in our natural environments, assuming that we all read the same article, or like an article of equal difficulty with equal length, who would get through it fastest, who would get through it slowest? I think psi would be slowest. Would it be worse to mix the papers or have them read about their field? Maybe we could control for some randomness, and like we could probably control for some tangents by just having all the papers outside of everybody's field. That would slow us all down, but it would reduce the chance that we would go on a paper-related tangent. So in some way that might actually be a cleaner study. Maybe I should have set that up as the study for this. Maybe I'll do that for the next one, for the next lecture that I have. Like the independent variable, or the factor would be VTuber, with the levels being me, psi, phi, z, and nep. And then the dependent variable would be words per minute. Throws judicial option cutely. Reading a particle physics paper after all. Please no. Please no. Oh, I found a good moral licensing paper. I'm kind of overwhelmed with all the stats streams, but I think after I get through all my stats lectures that I have planned and scheduled, I will get to the moral licensing paper, and I'm excited about it. I also remembered that I actually have a friend who, like, for a while, her expertise was moral licensing, and I want to see if I can get her to come on stream. But of course, that does risk you finding out who I am. You finding out my flesh identity, so maybe not. Maybe I can ask her to point me in the direction of somebody unconnected to me who would be willing to come on stream and talk about moral licensing. Yeah, I'm excited too. Okay, anyway, right, lecture. It would be neat, right? I would love to do that. I would love to do that. Okay, anyway. So, the means of the conditions are different. And there's two possible reasons that could be. Of course, the usual null reason is that it's just sampling error. The fact that the live action condition had a higher mean than the other two conditions means absolutely nothing. It's just noise, it's sampling error. The way that the teacher's presenting themselves actually has zero impact on the grades overall. Most of the time it is usually chat. The 3 word per minute was after I triggered like a 30-minute tangent by talking about Liechtenstein University. It's a very strange... I was there! And then we went on Google Maps and she looked around Liechtenstein University and stuff. I don't know if I'm pronouncing that right, actually. But yeah, I think most of my tangents tend to be caused by chat as well. So I'm just going to blame all of you. Even though it's me, I could be resisting, but I'm not. Okay. So one possibility is this is all sampling error. It's meaningless. It's not real. The other possibility, of course, is that it is real. Our independent variable did actually have some impact on learning, and that's why the means are different. Now, of course, this raises the question of how do we know? How do we know if this was sampling error or if this is a real difference, if our independent variable, our factor, actually did something? For t-tests, we calculated a t-value, and the t-value is pretty much like a ratio. It was the difference that we had between two sample means for the independent test, or like the difference between, or the mean difference for the repeated measures t-test, or the difference between a sample mean and the population. It's some difference. It's the difference that we found divided by the difference that we would expect to find by chance. So how much bigger was the difference we found relative to the difference we'd expect if nothing was going on? That's what a t-value is kind of doing. It's basically a ratio of what we found to what we'd expect to find if the null was true. ANOVA does something similar. ANOVA is also a ratio, but instead of t, it's an F ratio, capital F ratio. What this is the variance between sample means. In other words, how much do these sample means differ from each other on average, divided by how much variance we'd expect due to sampling error alone. So essentially, both of these tests are kind of doing the same kind of thing. They're calculating a ratio that's, here's what you found, divided by, here's what you would expect to find if nothing was happening. Is F the same as the F score? I'm not actually sure what the F score is. F score. What is the F score? A measure of predictive performance. Oh, it's kind of like D prime, it looks like. Yeah, no, this is something else. The F score is a measure of how accurately you're recalling things, it looks like. Precision and recall of test, where precision is the number of the true positive results divided by the number of all samples predicted to be positive following, but... Oh, is this... Yeah, well, either way, the answer to your question is they're different. They're different things. Yeah, this is a significance test. The other one seems to be some sort of measure. So this is trying to test a hypothesis. Oh, it's for how good a model is. Oh, it's like a model fit score. Oh yeah, in psychology we usually use like chi and chi-square and stuff like that to test model fit. At least that's been my experience. You can use ANOVA to compare model fit to see if one model's fits better than another. But usually rather than F score, we use chi-square in psychology in my personal experience. Yeah. Oh, by the way, model fit, it's like you create a statistical model to say, try and predict some outcome. So like, for example, yeah, no problem. For example, with this study that we're making, I might create a statistical model where I try and predict your score on the quiz based on which teacher you had. And then a fit score, like this F score or chi-square, is trying to quantify how accurately am I predicting this? Like, how often am I getting it right versus how often am I getting it wrong based on my statistical model? Anyway, okay. Putting that aside. So, we have this ratio that we want to calculate. We have the variance between our sample means divided by the variance we'd expect to find if this was just error, which means we have to figure out ways to calculate both of those things. So how do we do that? Well, first I'm going to start to the conceptual level about what's going on here. Here's the data again. The variance between our groups, the variance between our three conditions, is kind of predictably the variance between the average score in each condition. So we look for the variance between these three means, because these are our three conditions. There's our between group variance, so that is how we estimate the numerator of the F ratio. This is our estimate of how different our groups are. Then we have to estimate how different we think our groups would be just due to random noise. How do we do that? We look within the groups. How much do people differ from each other within each condition? That is our estimate of how much error we'd expect just due to random chance. Now, perhaps you are asking why. If you're not, I'm going to answer you anyway, but perhaps you are asking why. In each condition, so in the no video condition, in the live action condition, in the VTuber condition, in every single condition, people within the same condition are treated exactly the same. They all get the same lecture. They all see the same visuals. They all hear the same voice. But there's still differences in scores among the people in the same condition. And there's a bunch of reasons those differences could be. It could be individual differences. Like maybe some people in the no video condition have taken a stats class before, and maybe others have never taken a stats class before. Maybe some of them have test anxiety and others don't. Maybe some got a good sleep last night, others didn't. Just general individual differences. It could also be experimental error. I've kind of pointed out that the live action teacher and the no video teacher and the VTuber teacher are all different people. At least in this study design. That's not ideal because it could be that maybe one of these teachers is better at presenting the information than another teacher, and it's not the way that they're visually presented, it's how they're presenting the information. Even if they have the same PowerPoint, they might be explaining it differently verbally. So that would be experimental error. My experiment isn't carefully controlled enough. And it could also just be like within conditions. It could also be a matter of maybe some people are intimidated by the teacher, and maybe some people are calm from the teacher. Like maybe there's some, or maybe the teacher treats the students differently for whatever reason. Or experimental error might be maybe some people taking the experiment are having tech issues or something, right? And that might cause them to differ from one another. We don't know why people in the same condition are different from one another on our dependent variable. They shouldn't be. They all got the same treatment, so they shouldn't be different, but they are. In other words, variability within conditions is the variability we can't explain. It could be due to chance. It could be due to just other things that are completely out of our control and outside of our knowledge. So these people shouldn't differ, but they do. So they're the ones we're going to use to estimate our within group variance, our error variance. These people shouldn't differ. How much do they differ? That's the idea of error. It's just how much variation can we expect just due to randomness. Of course, the between group variance is a bit more straightforward. Like, it's how much the treatment groups differ from one another. And of course, there's two possible explanations for that. It could be, of course, that your independent variable did something, that the way that your teacher presented themselves actually did have an impact on learning. Maybe having a teacher on camera makes you learn better, or maybe having a teacher off of camera makes you learn better, or whatever. The other possibility, of course, is that it was just random chance they happened to be different. Like, it's something you can't account for, something that you didn't predict, something, or just like sheer randomness that caused that difference. And the idea of the F ratio is that if we divide the difference between conditions we found, the between group variance, by the within group variance, which is the variance we found where there shouldn't have been variance, then we can get a ratio of how much bigger is what we found to just random noise. So what ANOVAs are doing, and this is true for all the types of ANOVAs we're going to talk about, is it takes the total variability in scores on your dependent variable. So we had a bunch of different quiz scores, and it splits the variability, the differences between those scores, into two categories. The first is the within group variance, which is theoretically the way we're thinking about it. Those differences in scores are just chance. They're noise. They have nothing to do with our independent variable. They just showed up. We don't know why they're there. And then the other bit is between group variance. This is differences. There's still some noise in there. There could be some weird things between the groups that we didn't account for, but at least part of it, ideally, is due to our independent variable or our factor. So in this case, the way that the teacher presented themselves. And then we build them into this. There's your F ratio. And the way that this kind of looks is, you have the variance between treatments divided by the variance within, which represents the differences in your groups, including the effects of the independent variable, divided by the differences that you'd expect to find if the independent variable didn't do anything. You can further sort of simplify this down to the effect of your independent variable, the treatment effect plus some error on top, divided by error. With the idea being that if you have accurately estimated your sampling error, these two should sort of almost cancel themselves out, and you should be left with a number that just represents how much bigger your treatment effect is than sampling error. How much bigger is what you found than what you would have expected to find if the null is true. That's the idea here. How are we doing so far? Are we keeping up all right? Seems like there's a bit more latency in the stream than I would like, which is frustrating because I set it to the lowest latency. Or maybe that's just me. Oh yeah, no, I screwed it up a little bit. That's okay. We're fine. Yeah. Yeah, how we hanging in there? Everything okay? Making sense? Anything I can clarify? Or we'll just kind of make sense? Awesome. Yay. I'm glad. I think I'm following. All right. Cool. Guy. Hello, Guy. It's fine for now. Okay, sweet. It's all right. All right. I'm going to keep going then. All right. So now the idea here is that if the null hypothesis is true, if your independent variable did nothing, your groups are all the same, it's just error, then the variation due to your treatment should be 0. So essentially, your variation due to your independent variable, the differences between groups, there's nothing there. So you've got 0 plus error divided by error. So if your independent variable did absolutely nothing at all, you should just be dividing noise by noise. In which case, you should get an F value that is roughly 1, because you're dividing error by itself. You're dividing a number by itself. There's no treatment effect. So your independent variable does nothing. Your F value should be roughly 1, thereabouts. When there is a treatment effect, that makes more sense now with the first part of 0. Yeah, I'm hoping it makes a bit more sense now. I think this does help with the explaining what's going on. Like, this is some amount of variability here due to your independent variable, and these two are both supposed to be variability just due to randomness. So theoretically, these two things should be the same, even if we're estimating them a bit differently. So yeah, if your independent variable does nothing, you should be dividing just noise by noise. You should be dividing the same number by itself, and you should get an F value of 1. Yeah. Now, when there is a treatment effect, so if your independent variable does something, do you think the F value goes up or does it go down? Does the number increase or decrease if your independent variable does do something? It increases, exactly. If your independent variable does something, then the variation due to your treatment effect should be greater than 0. So this part of the equation here gets bigger, which means the numerator of your fraction is bigger. The denominator should be smaller than the numerator because you've taken this number and added something to it. So now the top should be bigger than the bottom. You should get a number bigger than 1. So if you reject the null, your F value will be greater than 1 because you've got more differences between conditions that can be explained by chance alone. This doesn't guarantee that you're going to reject the null. Oh, so you're not guaranteed to reject the null if your F value is above 1, but it's more likely that you'll be able to reject the null. Like, we want to be careful. We don't want to just say, like, we don't want to just, like, if it's greater than 1, we automatically reject the null. We're going to be a little more careful than that. We're going to have standards that are a bit higher than that. But it's more likely you're going to be able to reject the null if your F value is greater than 1. It's more likely that there's an actual treatment effect there. There, I'm ducking so you can see the slide. I need to start planning these slides with me in mind, but I think it's kind of fun to just peek over the edge of the slide, like, hi. Okay. All right. Now, around this time, or maybe even a little before this, the peeking over the edge is cute. Thank you. I think it is too. I think it's very cute. Okay. So, usually during this class, I will have at least one student who asks the kind of obvious question, which is, okay, well, like, that's great and all, but the ANOVA doesn't actually seem all that useful. Like, yeah, t-tests can only test for differences between two groups, but at least when they are significant, you know what the difference is. You don't need to do anything else. So instead of doing an ANOVA, why don't we just do a bunch of t-tests, you know? Like, an ANOVA compares 3 means. Why don't we just do 3 t-tests to compare group 1 to 2, 2 to 3, and 3 to 1? That seems more efficient. Well, there's a reason for that. There's a reason that the ANOVA exists, and not just like a bunch of t-tests. When we talked about sampling error, we observed that a single t-test, for a single t-test, just one, your type 1 error rate, the chances that you'll make a false positive, that you'll think something's there but it's not, is equal to your alpha level. And the standard alpha level in psychology is 0.05. So with a single t-test with an alpha of 0.05, your chance of getting a false positive, your chance of thinking that you found something when you actually didn't, is only about 5%. And we consider that 5% an acceptable risk. This is called your test-wise alpha. It's the likelihood that you will make a type 1 error in a single statistical test. But this is where the problem comes in. Let's say I run 3 t-tests. I do 3 different t-tests to compare my 3 groups to every other group. What's my type 1 error now? You don't have to give me an exact number, but what has happened to my type 1 error, my chance of making a false positive, when I increase the number of t-tests I'm doing? So if it's a 5%, not exactly, but about 15. Yes. And really good catch on that. Not exactly. It's not like multiplicative. It's not like it's going to go up to 15%, but it's definitely going to be bigger than 5%. I have increased my chance of a type 1 error. Great job, Astrologipos. Basically, this becomes my family-wise or experiment-wise error. This is your total probability of making a type 1 error, of getting a false positive across all of the tests you run. So if I just jump straight into a bunch of t-tests, I am really raising the chances that I'm going to get a false positive, that I think I found something when I really didn't. And when we talked hypothesis testing, we talked about why we're so concerned about false positives. Because our research can be used out in the world, this can have real implications for people's lives and health. And then, of course, there's like, even if it's not like a really like applicable to the real world bit of research, you just potentially wasted millions of dollars for a false positive. You know, like, just generally we want to avoid that. And this increases the chances that it will happen. So that's why we don't do a bunch of t-tests. We do an ANOVA first. So I know it's been, how long have we been going? We've been going longer than I hoped we would. It's been about 48 minutes, so let's do a check-in. Oops, there goes all the monies. Exactly. I'm gonna do a quick check-in. When would I use an ANOVA instead of a t-test? More than one factor. That is also true. That is also true, Maury. That's not quite what I was looking for here, but in about a week and a half, we will go into what happens when you have more than one factor, and that is also a reason why you would use an ANOVA rather than a t-test. So you're ahead of schedule. Astrologipos, comparing 3 or more samples. Exactly. Exactly. So if we have more than 2 groups, so 3 or more groups, you gotta use an ANOVA. Maury's been skipping ahead. Next one. Okay. Let's say I do an ANOVA. What number for my F value should I get on average if the null is true? Yeah. Set of experimental groups, not just a pair. Xenotime, you are also correct. All right, rewinding back to samples. Maury from the future. Okay. So in ANOVA, 1, correct, Astrologipos, exactly 1. If the null hypothesis is true, on average, we should get a 1 for the F value. Exactly, Xenotime. You got it right, too. Good job, good job. Because you've just got error divided by itself. A number divided by itself equals 1. So you should get 1, roughly. All right. Let's say I increase the difference between my groups. I move my groups means further apart. Will my F value get bigger or smaller? F will get bigger than 1. But generally, if I increase the differences between my groups, regardless of whether we're starting at the null or not, will the number get bigger or smaller? Yeah, it increased. Yeah, I knew that you knew the correct answer to that. I think maybe there was a miscommunication what the question was, but like I knew you knew it, so you don't time. Yeah, and Australopithecus, absolutely, it would get bigger when the differences between the groups increases. The numerator of your F ratio increases, so you get a bigger number. All right, I got another one. In ANOVA, I take the total variability between all the scores, the total variability in all the scores on our dependent variable, and I split it into 2 pieces. So let's start out with, what are the names of those 2 pieces? Oh no, I forgot the names. Yeah, that's fair. I realize y'all are less likely to be taking notes on this than my normal treatment effect and random stuff. Ah, that's what they represent. So Guy, you're on something. That is, you're on to something. Sorry, you're on to something. That is what they represent. But what are the names? What are the names of them? It's like the overall one and the treatment specific ones. Variance of sample means and variance due to error. That's what they represent. But those aren't quite the names. You know, I'll give it to you because you know what they represent, and that's what matters. The names are the between groups variance, which is the variability between your means, and the within groups variance, which is the variability within conditions. The between groups represents the effect of your independent variable and some noise, and the within just represents just noise. Now, how are these 2 things used in the F ratio? Which one goes on the top of the F ratio and which one goes on the bottom? So you've got your between groups variance and your within groups variance. Which one goes on the top of the F ratio and which one goes on the bottom? Between is on top, within is the bottom. Correct. Between is, well, between is the your factor, your independent variable plus some noise. Within is just noise on the bottom. Good job. And I have one more question for you before we keep going. Between is numerator, within denominator. Correct, Australopithecus. Exactly. All right, one more question. Why can't I just do a bunch of t-tests? Why do I have to do an ANOVA? Why? It would be so much more efficient to just do a bunch of t-tests. Right? The cumulative chance of type 1 error increases. Exactly. The more t-tests we do, or just generally, the more statistical tests we do, the higher the chance of a type 1 error. Because t-tests will make not an ANOVA, but a supernova and explode the planet. Quick, call Z! Can you imagine? Oh my gosh. If that was the case, my undergrads would have exploded the planet about 20 times over by now, probably. Oh no! Oh, scary. All right. We do math. We do math now. I'm not going to go too into the math because frankly it gives me a headache and I don't want to think about it too hard. But we're going to at least like go over the math a little bit. But yeah, you do more and more tests, the chance of a false positive goes up and up. Exactly. Exactly. Oh, actually, come to think of it, I talked about that in the BL fan brain scan video. What that paper was doing is they were testing to see if certain areas of the brain were related to being a fan of boys love content. ANOVA, I didn't know Mylan was doing horror stream stocks. It's not horror. It's not. ANOVA isn't even that bad. In fact, we're talking about possibly taking ANOVA out of the curriculum at my university because it's too simple and not a lot of people use it anymore. Funny how that works. It's really not that bad. Yeah, but yeah, the boys love paper stream or video. It wasn't a stream. What they did was they actually did 20 individual tests. I think it was 20 t-tests or something like that. I forget exactly what type of test they did, but they did 20 hypothesis tests without correcting for type 1 error. And based on an alpha of 0.05, guess exactly how many of those 20 tests did they reject the null on? So they did 20 tests. They used an alpha of 0.05. Exactly astrologos. They did 20 tests and they rejected the null on exactly one, which is exactly how many rejected nulls you'd expect if it was entirely type 1 error. Oh, that was such a weird paper. It was a preprint. It was not published, no. It was not published. It was a preprint. It was a really, like, I recommend watching the video. It was a really interesting paper because the main text of the paper itself, I had a lot of problems with it. And then I went and I read the supplemental material, and the supplemental material was basically incredible, actually. Like, all of the problems that I had with the main text were addressed in the supplemental material, but they were never mentioned in the main text whatsoever. Like, the main text was testing completely different hypotheses than it claimed it was, and it was doing really bad statistics. And then you go into the supplemental material and it's like they've written an entirely other paper that actually does test those hypotheses and does use appropriate statistics. And I was like, what happened to your what happened to your the RB writing a questionably statistically analyzed paper about Yuri to kickstart my psychology career? I'd make a video on that. We need balance. We need balance between the forces. Okay, anyway, let's do the math bit. Let's get the math bit out of the way. Again, I'm not going to go too deep into the math bit, but while the supplemental is sometimes pure gold, this is so true. And for that paper, the supplement was incredible. I was like, I wish this supplement was the paper because it is so much better, so much more informative, so much... It was so strange. It was so strange. I was like, how can these two things be the same? They were... Anyway, it was a wild ride, but that's not for now. That's something else entirely. So let's put that over there and let's get back to ANOVA. All right, so we've got some new notation here. We have T. Capital T. Yeah, there have been times when all the information I was the supplement and the paper itself had absolutely nothing of value. Yeah, that was exactly the vibes that this paper had. It was so wild. I've seen it before, but I've never seen it to that extent. I've never seen it to that extent before. The actual paper never tested the hypotheses that it said it did in the abstract or the introduction. It never did. It never even got close. It didn't even measure the variables it would need to test those hypotheses. But the supplement did. It was so strange. I've never seen anything like it. Okay, anyway, notation. T is the sum of all the scores in a single condition. So I take the sum of all of the stats scores in, say, the no video condition, add them all up, that is T. So in this case, we have 3 conditions, so we should have 3 T's. The total of all the scores in the no video condition, the total of all the scores in the live action condition, and the total of all the scores in the VTuber condition. G is the grand total. This is the total of all of the scores in the entire study. I take all of the scores on the stats quiz from every participant and I add them all up. That's G. Then we have K. K is the number of conditions you have, or the number of levels. I think for now we're going to say it's the number of conditions. This is going to get a little more complicated when we get to factorial ANOVA, but for now, K is the number of conditions. We had 3 conditions here: no video, live action, and VTuber. So K is 3 for the study that we're using for our example. Little n is the number of participants in each condition, or each cell. And the word cell, we'll use that again when we get to factorial ANOVA, but for now, nah. In this case, we had 5 people per condition, so little n is 5. Is G being bold significant? No. In fact, T is also bold, but you can't tell. T, K, and N are all also bold, but you can't tell as well for some reason. Just all of the notation, I bolded it here. Just to be like, this is the thing I'm giving you the definition of, but yeah. G being bold is not meaningful, other than I was trying to emphasize it. Bold means these are matrices, math, explosion noise. No! How could it be weird for it to be a vector? Yeah. Oh my gosh. This is what I get for not getting far enough in math. No, the bold is meaningless here. The bold is meaningless here. In fact, I didn't even know that bold could be meaningful for math. So if that tells you anything, ignore the bold then. Ignore the bold. It does not mean there's a vector. Sorry, I had the wrong SFX. Don't worry about it. Don't even worry about it. This is on me. This is on my lack of knowledge. Thank you, though, for telling me. I should fix that in my slides for, like, future lectures and stuff like that so that I don't confuse my mathier students. Thank you for letting me know. Bold means there are matrices. Matrix, the movie sounds. Oh, no. Okay. I've got more. So little n, lowercase n, in this case, the casing does matter. So lowercase n is the number of people in each condition. We had 5 people per condition, so lowercase n is 5. And then we have uppercase n. This is the total number of participants in our study. We had 3 groups of 5 people, so we had a total n of 15 people. Now this handy dandy thing here, this is the ANOVA source table, or the ANOVA summary table. Look at it. We are going to have to calculate the sum of squares for the between variance, the sum of squares for the within variance, and the total sum of squares. We're going to have 3 degrees of freedom now. We have the degrees of freedom for the between variance, the degrees of freedom for the within variance, and the degrees of freedom total. MS is the new name for variance. It's mean squared. We're going to have a variance between, that's our between groups variance that goes on top of the F ratio, and then a variance within, that's our within group variance that goes on the bottom of the F ratio. And then we have the F ratio. There is no F within or total, that isn't a thing, and there's no MS total. There's no total variance either. So that is our ANOVA summary table. It's going to summarize all the information we need for our ANOVA. So let's start calculating things out. To calculate the total sum of squares and the degrees of freedom, the formula for your sum of squares total is this. It is the sum of x squared, where x is each score. So first you square all of the scores on the dependent variable you've got, and then add all the squared scores together. There we go. G squared, so this is where you add all the scores together and then square the result, divided by the total sample size. So first, square every score that you've got. Second, add the square scores together. That gives you this sum of x squared here. So steps 1 and 2 get you this. Then you add every score together to get G, and then square the sum of all the scores. That gives you the top of this bit. Then you divide that squared total by the number of participants that you have, the total number of participants you have, big N. And then you subtract the result of this half from this. That's how you get the sum of squares total. The degrees of freedom total is a lot easier and a lot less tedious to do. It is your total sample size minus 1. So in this case, we had 3 groups of 5 people. We had a total of 15 participants in our study, minus 1. Our degrees of freedom total was 14. Much easier. There's another way to calculate the degrees of freedom total. If you happen to have the degrees of freedom between and the degrees of, where's my mouse? If you happen to have the degrees of freedom between and the degrees of freedom within and add those together, those will also equal your degrees of freedom total. So you can either just get the total number of participants minus 1 or add together degrees of freedom between plus the degrees of freedom within. They'll get you the same number. So let me show you how this is calculated out. And this is going to go real fast. I'm sorry. I'm going to do like the first condition just to sort of show you slowly, and then I'm just going to skip to the end. So here, the first thing that we need to figure out, well, How many participants do we have? We have 1, 2, 3, 4, 5 participants in this condition. So little n for condition 1 is 5. What's the mean? First, we add up all these. 0 plus 1 plus 3 plus 1 plus 0 is 5, divided by 5. The mean for this condition is 1. Our next goal is to get the sum of squares for this condition, which is each score minus the mean squared, and then add all that up. So it's the same sum of squares formula we've been using this entire time. X, the score 0, minus the mean of 1. This is going to be negative 1. 1 minus the mean of 1. It's going to be 0. 3 minus the mean of 1 is going to be 2. 1 minus the mean of 1 is going to be 0. And 0 minus the mean of 1 is going to be negative 1. Next, we square all those deviant scores, or those deviation scores. Negative 1 squared is 1. 0 squared is 0. 2 squared is 4. 0 squared is 0, and negative 1 squared is 1. To get the sum of squares for condition 1, we add all this up. So 1 plus 0 plus 4 plus 0 plus 1. Our sum of squares for condition 1 is 6. And then t for condition 1, the total of all the scores in condition 1, we already actually did that when we were calculating the mean. It's 0 plus 1 plus 3 plus 1 plus 0. It's going to be 5. And then you just do that for every condition. It's a lot. Oh my god. So this is, yes, okay. So this is calculating the total sum of squares. We're calculating the within group sum of squares now. Let's skip ahead. Here's the entire table filled out. Once you've got this, you can calculate the within group sum of squares pretty easily. So it's a lot of setup, but after the setup, it's simple. The sum of squares within is the sum of squares in each condition all added together. So you take the sum of squares for condition 1 plus condition 2 plus condition 3 plus however many conditions you have. In this case, we have 3 conditions. The sum of squares of condition 1 is 6. The sum of squares of condition 2 is also 6. And the sum of squares for condition 3 is 4. That threw me off. So you take 6 plus 6 is 12 plus 4. Your sum of squares within is 16. That is your sum of squares within conditions. I can feel my brain slowly shutting down. So my sum of squares within is 16. We never quite calculated the sum of squares total, but that's okay. I'm going to show you a little trick. Oh, but we did figure out the degrees of freedom total is 14. Total sample size of 15 minus 1 is 14. So we're slowly filling in this table. Now let's continue to calculate the within group variance. And to do that, you know, before our formula for variance could be written down, where am I? Where's my, there. Could have been written down as the sum of squares divided by the degrees of freedom. That's still true. So once we have the degrees of freedom within, we can divide the sum of squares within by the degrees of freedom within to get the variance within. So let's get that degrees of freedom within. The degrees of freedom within is the degrees of freedom for each condition all added together. Degrees of freedom for a single condition is the sample size in that condition minus 1. So we look down here for the sample size in each condition. Sample size for no visual is 5. We have 5 people who have no visual of the teacher. 5 minus 1. The degrees of freedom for this condition is 4. Live action, we have 5 people who had a live action video of the teacher. 5 minus 1. Degrees of freedom here are also 4. And that's actually going to be true for the VTuber too. We also had 5 people watching the VTuber minus 1 equals 4. I have a proposal for how to improve this. Don't say between groups and within groups. What should I say? BGWG? Betwixt groups and amidst groups. That is so much more fun to say, you know? Like, I heartily agree. I think my students would be absolutely baffled by that, and I would lose them. But betwixt is just such a great word, and I don't say it nearly enough. And amidst is like the kind of word that makes me feel like I'm gonna bite my own tongue when I'm trying to say it, that I'm gonna screw it up. I don't know why. I don't know why it's hard to say. It's only a 6-letter word. It's only 2 syllables. Why do I have so much trouble with amidst? It feels like one syllable is almost crashing into the other. Like the mouth shape you have from emit is hard to switch into the dist. Oh, is there? There's a fun linguistics reason it's hard? I think I remember something along these lines for like the name of this type of thing in linguistics back when I took a linguistics class, but that was over a decade ago, so I don't remember it. Yeah, it just feels like it's not. DST violates the sonority hierarchy. I'll have to look this up. I'll have to look this up after. I'm not gonna go on a tangent and look that up now, but I'm gonna Google it. The correct order is dits. I see. All right, I'm gonna look this up. I'm gonna read about this after stream because I really want to know. IDK, I say it fine. Maybe it's a skill issue. D and T are tied. Amidst. If I just ignore the D in there, if I just say amidst, that is a lot easier to say. But if I say amidst, that's harder. And I think they sound indistinguishable, which is the funny thing. Like, I'm pronouncing them differently, I'm moving my mouth differently, but I can't hear a difference. And one version's so much harder to say than the other. It's phonetically difficult to go down the hierarchy from D to S and then back up to T. Oh, it's kind of like a roller coaster. It's not like smooth sailing. You're not going like down or up. You're going... You're switching from going down to up. That's why it's hard. Yeah, that makes sense. That makes sense. Interesting. Linguistics is such a cool field. I wanna take more linguistics classes. There's so many classes I want to take. We need more VTubers. I wonder if I can convince people to become linguistics VTubers. There's that one linguist who I really, really love her work on the internet linguistics, Gretchen McCullough. I wonder if I could convince her to become a VTuber. I would make her a model. I'd make her a model. She has a podcast. Or I could just listen to the podcast. I could do that too. I'd make her a model. I'd make her a simple model. If I knew what she wanted, I would do that. I'm a huge fan of her work. Anyway, let's get going with it. Let's not get too sidetracked. So you calculate the degrees of freedom, and then you add together all those degrees of freedom. So that is 4 plus 4 plus 4. The degrees of freedom here is going to be 12. Another way to calculate it is if you have the total sample size. So we had 15 participants total. You have big N. You can subtract the number of groups. In this case, the number of groups is 3. We had 3 conditions, or 3 levels if you want to use ANOVA language. So that's 15 minus 3. That also gives you 12. Both of them will give you the same result. Whichever technique you use, you're going to get 12. So where okay. I'm gonna have to start toggling between slides. So our degrees of freedom within is 12. To calculate the variance within, we're using the usual sum of squares divided by degrees of freedom. In other words, sum of squares is 16 divided by the degrees of freedom of 12. So our sum of squares within is 16 divided by 12. It's going to be 1.33. So I'm going to fill that in. 16 divided by 12 equals 1.33. There's our variance within groups. That's our error variance. That's the variance that represents a non-terminating funny number. Indeed. I have some affection for infinitely repeating funny numbers. I don't know. I like them. I don't like irrational numbers. But I like these ones. They're just kind of like doing their thing, you know. They're just going off into infinity, and you know what? I support that. Welcome, Water Knight. It's good to see you. By the way, you totally changed my life with that scroll wheel thing. I'm still benefiting from it. I'm still giddy over it days later. I guess it's only been 2 days, but like, my quality of life has improved significantly. Anyway, let's get on to our between group variance. First, we're going to have to calculate our between group sum of squares. And this is a little weird. You might be like tempted to think it's just calculate the sum of squares of the means, but there's an extra step there that's a little weird. It's kind of like that. So the first thing you do is you use the usual sum of squares formula to calculate the sum of squares of your means. You have your means here, means of 1, 4, and 1. You calculate something called the grand mean, or the GM. This is the mean of your 3 means. So I take 1 plus 4 plus 1. I get 6 divided by 2. The grand mean is, or 6 divided by 3, the grand mean is 2. So the mean of our means is 2. Then we use that to see how far each mean deviates from the grand mean, the same way we would if we were calculating the sum of squares normally. 1 minus the grand mean of 2 is -1. 4 minus the grand mean of 2 is 2. And then 1 minus the grand mean of 2 is -1. Then we square those deviation scores so they don't all add up to 0. -1 squared is 1. 2 squared is 4. -1 squared is 1. So the sum of squares here is 6, but we're not done yet. There is a slight adjustment that we're making to the usual sum of squares process here for the between group variance. Or, sorry, we're still in the between group sum of squares right now. And that is, we're going to multiply that sum of squares that we just calculated, that 6, times the number of people in each condition to account for the sample size. So we had 6, or a sum of squares of 6, times 5 people per condition. We have 5 people in each condition, so 6 times 5 is equal to 30. And that is our sum of squares between. There's another way to calculate this. You can use this formula to calculate sum of squares between as well. It should give you the same number. There's also a third way to figure out sum of squares between. Sum of squares between can also be calculated if you know the sum of squares total. Once you take out the sum of squares within, whatever's left over is your sum of squares between. Typically, if I'm having my students do this for a class, I prefer that they use these last 2 methods rather than this top method. But, you know, follow your dreams. So our sum of squares between is 30. Let's plug that into our table. There we go. And now we can figure out the sum of squares total. The sum of squares between plus the sum of squares within equals the sum of squares total. So 30 plus 16, the sum of squares total is 46, so called because it's the total of between plus within. Now we need to figure out the degrees of freedom between. So basically using the complement rule. I don't know what the complement rule is. I've never heard that terminology. Complement rule. The sum of the probabilities of an event and its complement is equal to 1. Yeah, pretty much like the complement rule. I mean, it's like the same kind of concept, though. It's not the same thing, but it's the same kind of concept. You know, you have a set total and whatever's left over. So you have a set total, you take out one piece of it, and then whatever's left over must be the second piece. It's not quite the complement rule because the total isn't necessarily 1, but same kind of logic there. It's when you say something nice to a probability. That could work too. That could work too. We should be very nice to probability. Just like we need to be nicer to the null hypothesis. Oh, that's right. Someday I'll do a Valentine's event where I fail to reject the null hypothesis. That was not this year though. I missed my chance. Anyway. So the degrees of freedom between is the number of groups that you have minus 1. Our independent variable, or our factor, was presentation, the way the teacher was presenting themselves, and we had 3 levels, 3 groups. They had no visual, they had a live action visual, or a VTuber visual. The number of groups is K, and we had 3 groups. No visual, live action, and VTuber. So K minus 1, our number of groups minus 1 is 2. That is our between groups sum of squares. 3 groups minus 1, our between groups, or sorry, not sum of squares, degrees of freedom. Our between groups degrees of freedom is 2. 3 groups minus 1. Now you can probably guess how we're going to figure out our variance between. Our variance between is the usual variance. It's the sum of squares between divided by the degrees of freedom between. Sum of squares is 30 divided by the degrees of freedom, 2. Our variance between is going to be 15. Looking good. We're almost there. So here's the slide for that, if you were curious. And last but not least, we have to calculate our F value, right? The formula for the F value is what I've kind of been foreshadowing. It's the variance between groups divided by the variance within groups. In other words, our MS between divided by our MS within. So let's go back to our table. Here we go. Our variance between groups is 15. Our variance within groups is 1.33. What is our F value? If our F value is between divided by within, what is our F value? That's right, I'm saving this bit for you. 1.125. Yeah, I got something slightly different, probably because of rounding. I use the rounded versions, but if you use like 1.33 repeating, you might have gotten something a bit different. But yeah, roughly about, no wait, 1.125, or is it? I think the decimal's a bit off there. You're very, very close. Oh, divided the wrong thing. Oop. You're very close though, guy. I think your decimal's just one off. It could have been a typo. Could have been a typo. It's gonna be roughly, oh. If I use the rounded numbers and I don't go like with the whole thing, you know, the whole 3 repeating infinitely, it should be about 11.28, rounding to 2 decimal places. Roughly. Right around there. So yeah, guy was very close. 12-ish, yeah. If you want to put it that way, 12-ish, yeah. I think we're all roughly in the right area there. All right, good job, everyone. So we have completed our F table. Oh, I didn't divide the wrong thing. You divided the right thing. Good job. You should have more confidence. But even if you did divide the wrong thing, that's okay. I make that kind of mistake all the time. I'm not nearly confident enough in my German to try and pronounce that. But I kind of wanna. But I feel like somebody who knows more German than me would attack. Not really, but like I feel like my father took a lot of German classes, and I feel like he would be deeply disappointed in me if I got that wrong. That would be funny though. Zwölf. It's not too bad if you remember that. Yeah. I know that at least. Yeah, because what's his name? There's this Zwölf. Yay! That's not terrible. Yay! But yeah, one of the founders. So I'm a social psychologist, right? And one of the founders of social psychology is his last name is spelled Lewin. And I need to remember that it's Levin or something like that instead of Lewin. I don't know how to pronounce that stuff. Definitely in the top 95% of Americans. Yay! I'll take it. I'll take it. Oui. What? Okay, Zwölf. Zwölf. Zwölf? Zwölf? It's, like, say E, keep your lips in place, say O. Yo. Zwölf. 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 I have no confidence. I can't do it. I'm sorry. Eh. So like how Japanese pronounces E. Eh. Zwölf. Or yeah, Spanish. Japanese and Spanish have really similar vowel pronunciation. Zwölf. I can't. I'm cringing at myself. I'm gonna think about this at 3 a.m. and I'm not gonna be able to sleep. I think I need to listen to it. I think I need to hear it. Ew, 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 Zuel. I'm gonna listen to it after this. I mean, it became 12. Okay, I'm gonna listen to the pronunciation after this, and I think if I hear it, I could somewhat okayly mimic it. I definitely won't sound perfect, but I could do it better. So it's pronounced surprisingly similar. All right, all right. Thank you. Thank you for your mercy. I've never taken a German class, and I haven't heard much German either, it's possible that, so there's this interesting phenomena, in psychology of language, and I don't know if this extends over to linguistics, but like, if you don't hear certain phonemes or certain sounds at an early enough stage in your development, your brain can't process them properly. And it's possible that I just didn't hear that sound early enough on in my life, that maybe even if I did hear it, I wouldn't be able to, like, my brain wouldn't be processing it the way it really is. I don't actually know German, but I learned a lot as a kid and lived in Germany for a while, so I know barely any words, but my pronunciation's actually pretty good. That's a good place to be in. That's a pretty good, I mean, like, pronunciation is a pretty big battle for some languages, right? So, I mean, that's good at least. Like, if you see it written down, you could probably read it out to some extent, right? Mm-hmm. You have heard it, you don't recognize it spelled like that, though. That's also that's also possible. Took a German class back then. They taught us the ABC rap in the start and then how to start verbal fights by the end. None of my language classes were nearly that exciting. I only ever took Spanish and I've forgotten all of it. I'm honestly really ashamed. Oh yeah. Rico, welcome. Why are all the medical people scared of ANOVAs? You're the second person with like medical related knowledge that is concerned. ANOVAs aren't that bad. ANOVAs really, they're really not that bad at all. Like, yeah, they're kind of a pain to calculate, but they're just, I don't understand. I don't understand. I feel like there's a story here that I haven't heard. I feel like there's a story here, and I want to know what the story is. Why are we so upset about ANOVAs? The trauma? What trauma? It's just ANOVA. It's just it's really not that bad. I'm not teaching you like multi-level modeling or hierarchical regression with its random intercepts and random slopes and stats hurt me as a young Mothman. But I admit, stats hurt me a great deal as a young Mothman in undergrad. And I just so happened to have an incredible stats teacher in grad school, so maybe I didn't have a fair experience. If you had asked me before I went to grad school how I felt about stats, I would be very much in it with you, Rico. I absolutely would. Actually, really funny story. I was on a train in Germany and a person didn't realize I didn't actually know German because I spoke to them well enough and I just stood there awkwardly until they realized. That's funny. Trauma bonding all up in here. That's how my first year grad stats class, we described it as trauma bonding. Like, we got along really well during that first year because all of us were going through it together. I feel like stats is often taught really badly. I think it's hard to teach. I think statistics is hard to teach. I really enjoy teaching statistics, and I think I'm decent at it. I don't know if I'm doing as well with these lectures as I do with when I'm teaching in-person lectures. But I think I'm decent at teaching it. Students tell me I'm decent at teaching it, but I think the only reason I'm decent at teaching it is because I started out really bad at it. I think, there's that thing like you learn best through teaching, I think is part of it. And also, like, because I sucked at stats when I first took it, I feel like I have a better understanding of which parts are hard to explain. But I worry that I'm losing that. The longer I teach stats and the better I understand it, I think I'm losing my ability to remember which parts of it were difficult. I just plug in the numbers of the program and it goes brr. I don't want to remember the formulas. You don't have to remember the formulas. Exactly. I also plug numbers into the program and it goes brr. But I also want to be able to understand, like, if the program spits out something that doesn't make any sense, I want to be able to understand enough of what's going on beneath the hood to figure out where the program did something weird, you know? My German trip had only one instance of speaking German, and it was just ordering ice cream. The rest was watching Glee and Jurassic Park 3 and a lovely trip around Cologne. The cathedral was Augsburg. Sounds nice. But you can recognize what people are struggling with even if you get it all too. That's the goal. I can usually do that, but I think I'm getting worse. I had a hard time with pharmacology math already. I actually am really bad at math, Rico. Like, I suck at math. I suck so much at math. I will screw up simple math constantly. I think, and yet here we are exactly. That's why I will fight anyone who calls stats math, because stats involves spooky complex numbers. Didn't realize Cologne and Cologne are different cities. Three spooky, 5 makes sense. Oh my gosh. Okay, anyway, right. We're getting towards the end. We're getting towards the end. So let's keep going. Okay. So our F ratio was 11.28. There we go. Looking good. Looking good. So just to remind you where we're filling this all in, the between-subjects sum of squares is calculated looking at the variance between your three conditions, the means of your three conditions. The within-subject sum of squares is based on the variance within your conditions. You add up the sum of squares from each condition, and that gives you your sum of squares within. Oh, maybe. Cologne. Clone. Cologne. Kitty's getting restless. It's not dinner time yet, Kitty. You've got another 15 minutes or so. Okay. Let's get through this though. So Mr. Kitty can be prepared for dinner when it is time. All right. I so wish I could send voice messages in YouTube chat. I know, right? I wish so too. This would save me so much embarrassment. I get most of my German geography from EU4. Fair enough. Okay, right. The sum of squares total is derived from the sum of squares between plus the sum of squares within. Your degrees of freedom between is based on the number of conditions you have. It's the number of conditions minus 1. And then you use the sum of squares and the degrees of freedom between to get your variance between. The degrees of freedom within is based on the number of people you have in each condition. And then your variance within is based on the sum of squares within divided by the degrees of freedom within. Your degrees of freedom total is the sum of all of your degrees of freedom between plus within. And your F value is your variance between divided by your variance within. So the variance between your groups divided by the variance inside of your groups. Ba, ba, ba. Ba, ba, ba. There you go. Okay. So now let's talk about the F distribution, which is what we're going to use to figure out if we reject or fail to reject the null. I get to move down here again. I get to be real tiny. The F distribution is at just the T distribution squared, which blah. Because it's squared, that means all F values are going to be positive. We don't have that normal distribution like we did for T. We don't have like, blah, blah, blah. Give me my pen. I want my pen. It's your pen. The T distribution looked like this because you had half positive and half negative T values. Here, though, this is the T distribution squared. F values are always positive. This is actually what happens to the T distribution when you square it. This is what happens to a normal distribution when you square it. It becomes positively skewed like this. Now, if there is no treatment effect, if your independent variable has zero impact on your dependent variable whatsoever, the average F value should be about 1, because you're dividing error by error. So the peak of the F distribution is at 1. Most F values, if the null is true, should be 1, because you've just got error divided by error. So theoretically, you shouldn't be able to calculate an F value that's less than 1, but of course the real world is a messy, messy place. So you will sometimes get F values that are less than 1, but theoretically the lowest possible F value is 1. Theoretically. In reality, it can be less than 1, but meh. If your F value is greater than 1, there's a chance you can reject the null. But of course, it's how much above 1 does it need to be for you to reject the null? Mr. Kitty? Mr. Kitty? He's singing. He's got songs. Good boy. I'll be with you soon. We just gotta finish telling these people about ANOVAs. Maybe I should let Mr. Kitty teach. Like I said, he's seen me teach this class at least twice. Mr. Kitty, do you want to teach them about ANOVAs? Unfortunately, he doesn't speak English. Or any language that any human could understand. But maybe he could be a good teacher. He's a good boy. Okay, anyway. So we need to figure out how far above 1 is enough to reject the null. What are our standards for rejecting the null here? How big does our F value have to be for us to conclude there is a difference? Can he pronounce Xenotime, you keep like stun locking me. I don't know how else to explain. It's like the second I see that character, I have to start trying to pronounce it, and then I realize that I'm probably embarrassing myself horribly, and then I just kind of want to lay down, and then my brain just shuts down to prevent myself from overthinking, and then I just stare into the distance for like a minute, and like I know you probably have zero expectations that I try it every time, but it feels like a challenge, and then I'm never quite up for, like, I feel like I need to rise to the challenge, and then I try, and then, like, my brain shuts down. This is a me problem. This is a me problem. I need to slowly start trading in the mountains to become immune to this, and also just listen to the sound that makes on loops. Ooh? I don't know! I don't know what the hell that sound. Maury, you were supposed to be my ally. Maury, can you pronounce that? Can you pronounce that sound, Maury? Am I making too much noise? Am I quiet? Okay. No, that's why I'm asking help me. This is a stats class. This is a stats class. This is not a language class. I can't speak anything but English. I will speak the language of stats. Say E, then stop talking, but keep your lips. Okay, I'm locking in. We're going to finish this lecture. We're going to finish this lecture. We're going to do it. We don't want to make Mylan teach stats in German. Please no. Please no. If I ever do like another charity thing and I have, or like a punishment stream, like Psy, we can have me read stuff on irrational numbers and try and do something in German. No, I do not have time to learn enough German to do a stats lecture by Wednesday night. I don't. Please have mercy. I'll hire somebody else to do it for me. I have German friends. Okay, so to figure out if our F value is big enough to reject the null, to conclude that something's going on, we need to use another table. That's right, this is statistics, so we're using a table. For this, we need degrees of freedom, as per usual. The first set of degrees of freedom we need is the degrees of freedom between. This is also referred to as the degrees of freedom numerator because it is used to calculate the numerator of our F ratio. Here's the degrees of freedom between. It was used to calculate the numerator of our F ratio. We'll also need the degrees of freedom within. This is also called the degrees of freedom denominator because it was used to calculate the denominator of our F ratio. We're going to ignore the degrees of freedom total. We're not going to use that here. And we also need our alpha level. Our degrees of freedom between was 2. Our degrees of freedom within was 12. And our alpha level, we're using the standard psychology alpha of 0.05. The degrees of freedom numerator is used to determine which column of the F table you're in. So we go to the column labeled 2. So degrees of freedom between determines the column you're in. Degrees of freedom within, aka the degrees of freedom denominator, determines which row you're in. So we go down to the row labeled 12. Now, you'll see that there's 2 possible critical values here. This is how the F table deals with having multiple alphas. The bottom one, the bolded one, is for alpha of 0.01. The top one, that's not bolded, is for alpha of 0.05. Our alpha is 0.05, so we are using that top number there. And I know you probably can't see it, it's probably too small, but this number here, second column, 12th row, top set, our critical value is 3.88. In other words, our F value needs to be bigger than 3.88 for us to reject the null. So let's see if it is. Here's our table. Our cutoff is 3.88, so we need to be further in the tail than 3.88 to reject the null. The F value that we calculated is somewhere out here. It's 11.28, roughly. Do we reject or do we fail to reject the null? Reject, correct. We get to reject the null hypothesis. Good job, everyone. Yes, we reject the null. Our F value is bigger than our cutoff. We reject the null. This ratio of what we found to what we would expect to find by chance, the difference we found between our conditions was like 11.28 times bigger than the difference we'd expect to find by chance. That is a really big difference compared to what we'd expect if the null was true, so we reject the null. It would be very unlikely to get this result if the null was true. Now, effect size for ANOVA. I'm going to introduce you to a really bad effect size. Maybe not really bad. This isn't great, but it's easy to calculate, which is why it's the one that I teach, but there's other effect sizes for ANOVA that are better than this. So keep that in mind. You probably won't see this one out in the wild. You might see variations of it out in the wild. But the effect size is called eta squared. That's ETA squared. Written like this. It's sometimes also called capital R squared. Eta squared is trying to estimate the proportion of variability in your dependent variable accounted for by the independent variable. How much of the differences in quiz scores can be explained by which condition, which visuals you had. Now, the problem with eta squared, the reason I said it's not a great effect size is because it's biased. It tends to overestimate the actual effect size. It gives you a number that is too big, bigger than the actual effect size, which is why it's not that great. It's not like commonly used. Sometimes you'll see partial eta squared or generalized eta squared in the wild. These are variations of eta squared that are a bit better than just plain eta squared. Other effect sizes for ANOVA include omega squared, but I'm talking eta squared because it's easy to calculate. Eta squared is calculated as the sum of squares between divided by the sum of squares total. And this might be a hint as to why it's a bit biased. The sum of squares between isn't just the differences between your conditions. There's also some error in there. So you're treating your error as if that's part of the effect of your independent variable, which is why eta squared gives you a number that's bigger than it should be. But at least it's easy to calculate. So in this case, our sum of squares between was 30. Our sum of squares total was 46. 30 divided by 46 gives us an eta squared of 0.65, which would be telling us about 65% of the variability or differences in test scores can be explained by, not the difference temperatures of the room, that's wrong, by the visual of the teacher, whether you had a live action or a VTube or no visual of the teacher whatsoever. But that 65% is probably an overestimate because that's what eta squared does. It overestimates. As far as reporting this in APA style is concerned, here we go. The statsy bit of it, so up here is the table that we calculated earlier. The statsy bit of it looks like this. You have F, because now we're doing an F test, and we use the F table, of degrees of freedom between, so this bit, comma, degrees of freedom within, so this bit, so people can use this portion to figure out where you use the F table, and you looked in this column and this row for your critical value, for your cutoff, equals the F value that you calculated. And then the usual p-value effect size. So for this particular ANOVA, it would look something along the lines of F on 2 and 12 degrees of freedom was equal to 11.28. Our p-value was less than 0.05, we rejected the null, and eta squared was 0.65. About 65% of the variance in test scores could be explained by which teacher presentation you had. But that number's probably a bit too big because eta squared tends to overestimate. Whew. Now let's add the sentence to it, because again, one of the most important things you can do after doing stats is put it in plain language that people who haven't taken a stats class can understand. So here, a one-factor ANOVA, meaning we only had one independent variable, with visual presentation, and so that's my overall factor, my overall independent variable, and then my levels, no visual, live action, and VTuber as the independent measure. So there's my independent variable here. And test scores is the dependent measure, there's my dependent variable there, indicated that there were differences, that's me indicating in words that I rejected the null, in test scores among the three conditions. I did an F test in ANOVA with 2 and 12 degrees of freedom. I got an F value of 11.28, I rejected the null, so P is less than 0.05, and my eta squared is 0.65. This is a full APA write-up of the ANOVA that we calculated. Has the independent variable, has the dependent variable, and whether we found a difference. But you'll notice it doesn't say what difference we found. It says we found there was some difference among these three conditions, but it doesn't give you any more information. Because again, ANOVA can't do that on its own. ANOVA doesn't tell you where the difference is, it just says that there is a difference. Your back phone died. Welcome back. Welcome back. Happy to have you. So we know that there is a difference between these three groups, but we don't know where it is or how many difference there is, so we're going to have to do some additional stats. We're going to need to follow up our ANOVA. We're going to need to do 3 additional follow-ups. We have to compare the no visual to the live action condition, the live action to the VTuber condition, and the no visual to the VTuber condition. And we're going to talk about how to do that on Wednesday, but for now, here's all the new notation that we used. That's a lot. And yeah, we'll follow up on this on Wednesday with pun completely accidental. How to follow up a significant ANOVA. What to do if you reject the null on an ANOVA. How can we figure out what's going on there? What to do if your metaphorical metal detector goes off. How do you figure out what's under that sand? All right. How are we doing? Questions, comments, concerns? Anything like that. My voice held out. Do you eat a square? What kind of square? Is this like a square brownie? Like a brownie square? I would eat it if it was a brownie. Eta squared. Puns. Every day I suffer. And for what? For what? Only good flashbacks, Rico. Only good flashbacks. That wasn't so bad, right? That could have been worse. Could have been worse. Oh, thank you, Bushi. I'm really glad. I'm really glad. That's my goal. That's my goal. I try and make it make as much sense as possible. And later on, I will be going to I would like to later on go on to Rico land, or, well, my personal land, more like it, where I just use a statistical program and then show you how to do an ANOVA and that. Oh, I'm glad it's good to review. But yeah, I do all my stats these days in R, so I'd also like to do I haven't calculated a statistics by hand in years. That was really helpful and understandable. Thanks. Are the complex... Oh, no problem. Thank you, Xenotime. Thank you for coming. Are the complex portions of a wave equations physically real or a mathematical tool we use for expressing the complexities of physics in a mathematical framework? Yes. But also no. And furthermore, it depends. That was a good answer, me. You did good. I would argue, generally speaking, I would argue a lot of. Thanks for letting me be an agent of chaos, spewing tangents in my way. No, it was fun. I had a lot of fun. I had a lot of fun. Thank you. Yes, but no, but it depends was my favorite answer to Is This a Crime? I think that's true. This is really interesting. I'm glad. I'm glad. I had a lot of fun, and it was a good time. But if I took that question seriously, astrologicals, obviously I don't. That's completely out of my area, and I have no understanding of it. But I'm with the general belief that most of the things that we come up with for like how we think are just us trying to make sense of a world that may or may not actually have any underlying laws to it. Science rests on the assumption that the world has underlying laws, but also we're trying to interpret a very complex situation and complex set of phenomena that are interacting that have a lot of things that we probably aren't aware of or can't measure yet. And we're trying to filter that through how humans think about things. And we also know that we are not inherently rational creatures, so yeah. I think the answer is generally A, kind of, but also not so, yeah. I think it's like that best fit model kind of deal that we were talking about earlier. Like, it might be the model that works best that we have right now, but does that model actually reflect some does it perfectly or even generally well reflect the underlying phenomena? And does it account for everything? That's another question entirely, but I don't know. I don't know anything about that. And I'm just taking it seriously for kicks and giggles. I'm gonna go look up how umlauts affect pronunciation now. And also feed the cat. I'm gonna feed the cat. That's the first important bit. He's so cute. You are a handsome prince. I slow blink in your general direction, Mr. Kitty. Oh, he slow blinked back at me. Cat will always get mentioned. He's such a good boy. He's such a good boy. Oh my gosh, I love him so much. Yes, one day I will show you the cat. Oh my gosh. Oh my gosh, I love you, Mr. Kitty. You are so cute. He's doing literally nothing. But I gotta feed him. Okay, I'm gonna go feed the cat, and I'm gonna look up how to pronounce these things, and I'm gonna read up on sonority hierarchy, and I'm gonna go to sleep. Thank you all so much for coming to the stream today, everyone. I had a lot of fun. I enjoyed the tangents as well. I have two methods of treating my cats. You are my heart, my soul, my being, and why must you be the bane of my life? No in between. Bushi, unironically same. Unironically same. I think that is the universal cat experience. But right now, he's my heart, soul, and being. Oh, thank you. Thank you all for coming. I'm going to go give my cat a little kiss right between his little ears and give him some food. Have a good night, everyone. Take care. Bye.